This is a demonstration of GreenThumb, a Superoptimizer construction framework. What is Superoptimizer? Superoptimization is a technique to optimize code fragment by searching through the space of all possible instruction sequences. This technique is very useful. For example, it can be used to automatically generate people optimizations, to avoid buggy manually written rules, or missing optimizations entirely. But it is difficult to build a Superoptimizer. First, because the search space is huge. So in order to build a practical Superoptimizer, we need a very fast search technique. Second, we need to be able to prove that the output program is indeed equivalent to the input program. And this is typically done by translating programs to logical formulas and use SMT solver to do the proof. But this means the developer would have to deal with very complex SMT formulas. GreenThumb addresses these issues by providing an efficient search strategy that can be reused for any instruction set. It does not require developers to write a translator from programs to logical formulas. Instead, it uses Rosette, a solver-aided language embedded in Racket, to provide equivalent checker for free when the user implements the ISA functional simulator. Therefore, the framework is built on top of Racket. The search strategies run multiple search instances in parallel using different search techniques, including symbolic, stochastic, and enumerative search. Symbolic search uses SMT solver to perform the search. The stochastic search performs a random walk, and enumerative search enumerates all possible instructions but with a lot of clever pruning techniques. These search instances communicate about the best program they found so far and work collaboratively. Today I'm going to build a Superoptimizer for LLVM from GreenThumb. But first, let me show you the Superoptimizer I built optimizing a program. This is the program we try to optimize. It is a program that rounds up the number to the closest power of 2. It has 12 instructions, and this is generated from Clang 03. Let's see if we can optimize this program further. I'm going ahead and run the Superoptimizer on this program. At the beginning, it will print out information about search instances. Here it says that it's running one stochastic search instance, one symbolic instance, and 2 enumerative search instances. And hopefully it will find something soon. Here it prints out the message saying that it actually finds an implementation with the 4 instruction, and then the enumerative search is the one finding the solution. Here is the output program. Only 4 instruction. You can see that it's utilized this count leading 0 instruction. So the goal of the demonstration is to build the Superoptimizer that is able to optimize this particular program. But instead of starting from a relatively big program, we're going to start with a smaller program. This program clears lowest 3 bits, and we're going to use this as a running example throughout the demo. First, we have to understand the architecture of the framework a little bit. Here are all the important components, and we have to extend the yellow parts. First step, we can run this provided setup script given the name of the ISA, and it will generate a directory with the same name. Inside there are these files that are used for extending those components, and we have to implement some of the functions in these files. First, we're going to extend the machine component, where we have to define basic description of the ISA. In particular, we have to define the instructions we want to support. In the demo today, we're only going to deal with 32-bit arithmetic and logical instructions. no memory accessing instructions. Because of this, the program state representation can be very simple. It's just a vector of variables values. In the running example program, there are 3 variables in the program. So the program state is just a vector of length 3. Now we're going to define such information in the LLVM machine. You can see that the name of the file corresponds to the name of the component in the slide. Oh, right. I should actually open that with Dr. Bracket. As I said earlier, first we have to define the instruction we would like to support. I'm gonna go ahead and copy the instruction I want to support. And we have to define the program state. Here the script generates the default program state, which is a vector of the certain length, and this is what we want, so we don't have to modify anything. Now we're done with the machine component. We move to the next one, which is parser and printer. GreenThumb provide a default instruction representation, which is struct int with 2 fields of and args. We're gonna use this instruction representation to represent program. GreenThumb deal with 3 levels of program representation: source, string IR, and encoded IR. And we are responsible to write the functions to translate from one to the others in the parser and the printer. But instead of showing you how to implement these functions, which are not very interesting, I'm going to copy the implementation I already have prepared into the current directory. Now we can move on to the next step, which is the simulator. So I'm going to open LLVM simulator, and here we are going to implement this interpret function that takes in a sequence of instructions, an input program state, and it should output the output program state. I'm gonna copy in some code. In here, I copied the input program state into out, and then at the end I'm gonna return out as an output. The main loop of the program iterates all instructions in the program and apply interpret ints on each of the instruction. Interpret ints will extract the opcode and the arguments of the instruction. And then we have this switch statement. First is compare op to no op. If that is true, then we don't have to do anything. If op is equal to add, then it would modify the output state by applying this bit vector add function. Now I use XXX, which I'm gonna define later, but XXX means that add takes in 3 arguments and all of them are variables. Now I have a different variance of add. This variant takes in an immediate constant as a 3rd argument. Now we have to define this XXX and XXI. Here's my XXX. What it does is applying the function f to the value of the first input argument and the value of the second input argument. They both variables. Then we save the result into the destination output variable. I can define XXI very similar, but instead of applying the function on the value of the variable of the second input argument, it's just a constant. So if we only have 3 instructions, this is all we need for the interpret function. But of course we need more than 3 instructions. So I'm going to copy the complete implementation of this function into this file. here is the complete implementation. You can see that it's still pretty short. Second thing we have to do in this file is to implement this performance cost function that takes in the program, and it should return the cost of the program. I'm going to implement a very simple cost model, which is just the length of the program. And we are done with the simulator. Next, we have to enable some search techniques. Symbolic search is the one that it's easiest to enable, so we're gonna do that today. In fact, it's so easy that we don't have to modify anything when we use the default instruction representation. That means we should have a working Superoptimizer for our LLVM now. So let's try to optimize some program. The setup script also generates this very handy file test search that can be used to test each of the search techniques during development. In here, I can copy the code I would like to optimize. Here's our clearing 3-bit program. We also need to tell the Superoptimizer what is the output of this program, which is essentially the out variable. Okay. Alright, now we're ready to optimize this program. It is running, and now within 4 seconds it found this implementation with only one instruction. Awesome. Now we can try to optimize the bigger program that we optimized earlier in the demo. However, I know that the symbolic search is actually quite slow, so it wouldn't be able to optimize that program in time by the end of the demo. So instead, I'm going to cheat a little bit. I noticed that the output program of the optimization we optimized earlier have the same first and last instruction as the input program. So I can tell this information to the Superoptimizer by saying that, alright, I'm going to fix the first instruction by saying that that's the prefix of the program I want to optimize, and then I'm only going to optimize that middle part of the program. And similarly, I would fix the last instruction by giving that in the postfix. And now we're gonna synthesize up to 2 instructions for the middle part. Since we're dealing with a bigger program, I'm going to use a compressed version to represent program, and we have to provide more entries in the program state. Alright, now we can try to optimize this program. Alright, very quickly it found this optimized program with 4 instructions that we've seen earlier at the beginning of the demo. It also used this count leading 0 instruction. So I would call this as a success. However, if we have time to implement the enumerative search, we'll be able to synthesize the entire 4 instructions within 10 seconds as we've seen earlier. And we don't have to even tell the Superoptimizer to fix some instructions at all. Last, I want to end my talk with some use cases of GreenThumb. We use GreenThumb to build Superoptimizer for ARM to optimize basic blocks from wireless system and embedded benchmark suite. We obtained up to 80% speed up on some benchmarks. And I want to emphasize that we wouldn't be able to find some of these optimized programs if we don't use all the search techniques together collaboratively. We also built a Superoptimizer for green arrays, which is a stack-based 18-bit processor with 144 cores, very different from ARM. This demonstrates that GreenThumb can support very diverse types of processors. And this is GreenThumb. It is available on GitHub. Thank you.